And so we saw that by using our microscopic entropy model for the monatomic ideal gas, we were able to get the same results that we got from classical thermodynamics. So that's fairly reassuring. But what's also useful about developing these microscopic entropy models is it also gives us insight into cases where gases don't behave ideally, right? And when we do need to consider molecular interactions or the fact that the molecules take up space. Okay? And so just to reiterate, for a monatomic ideal gas, we saw that omega n was this. So I'm going to call this omega ideal gas. Right? And we saw there was just 2 pi m raised to 3n over 2 divided by n factorial, 3n over 2 factorial, h raised to the 3n, and then that was multiplied by v raised to the n, and also u 3n over 2. All right, this is what we got for specifically omega, not s. So this is just omega. Okay. All right, so that's what it was for an ideal gas. And for an ideal gas, the two main assumptions were that the molecules don't interact with one another and that the particles can overlap one another. All right? So that's for an ideal gas. And so if we actually wanted to, describe non-ideal gases, we would have to figure out ways to describe those molecular interactions or the fact that the gas molecules have volume. Okay? And so, generally, we call those non-idealities. So, actions excluded volume. All right, and so to account for these non-idealities, all we need to do is just modify this omega equation. Okay? So can modify omega. Right? And so there's many different ways you can modify omega to account for molecular interactions. And so that's actually where we're going to be exploring in the later part of the course. But for now, I just want to share with you one example of a non-ideal gas model. So one kind of fairly simple non-ideal model is the van der Waals model. So this is for a monatomic gas again, so argon or helium. And so for this omega VDW, it's basically almost the same as the result for the ideal gas, except in the volume term, you're going to subtract it by NB. And that's because this accounts for the volume of the molecules. Okay? And then for the internal energy term, you're going to add to it a n squared over v. All right? And so this accounts for the molecular interactions between the molecules. All right? And so that's really the only difference between the van der Waals model and the ideal gas model for the omega, for that multiplicity, for the number of different ways that molecules can arrange themselves in the system. Okay? And so having these definitions is useful because what we're going to do in Chapter 6 is we're going to take these equations and we're going to use them. So various non-ideal omegas. We're going to use those to develop pressure, volume, temperature relationships or equations of state. For non-ideal gases.